Good morning, everybody. My name is Julia Kregenow. Welcome to Astro 1. These are some of the questions we will be answering this semester. Do stars last forever, or do they die? Where do stars come from? Are they born? Yes to both, by the way, dying and being born. What is a black hole? How big or small, as it turns out? Where do they come from? Do they last forever? What was the beginning of the universe like? How big is the universe? Is that changing? Will it last forever? We're getting to some questions where the answer is we're not sure. And I'll point out when that's the case when we get there. And perhaps my favorite question of the semester, are we alone? I'm talking about aliens. And that's one of the questions where the answer will be, we're not sure yet, but I'll tell you how we're looking. If you find any of these questions compelling, then you are in the right class. Again, my name is Julia Kregenow. These are your learning assistants for this semester, and you'll get to know them as the semester goes on, but I just wanted to point them out. They have these handy name tags. They'll be joining you during each lecture period to help with some of the activities we do in class, and they'll also be available outside of class and before and after class and during any breaks that we might have to answer your questions, such as technical questions about the flipped app that some of you have already signed up for. That's great. This is Allison and Hannah. They took this class last semester. So they're you plus 4 months. All right, I'll let you guys sit down now. You don't have to stand there the whole time. Let's start with a question. Don't answer out loud. We're going to answer using these voting cards that are on our to-do list, which many of you probably already had one handed to you. I'll take a moment. If anyone does not yet have one of these colorful ABCD voting cards, raise your hand, and I will ask our LAs to give you one. If you're toward the back, you can just grab one off the back table. There should be a stack there. But if there's anyone near the front, let's make sure everyone gets one. I want to find out, by asking you this question before I tell you the answer, what insight you may or may not have about some of the objects we'll be learning about this semester. And no astronomy prerequisite is expected for this course. So you're not expected to know what any of those are yet, but I want to see what your intuition tells you. So here's how we will use the cards. And actually, Hannah, if you could give me one too, so I can demonstrate. We'll always use them with multiple choice questions. Raise your hand if you've used clickers before in a class at Penn State. Okay, this is a low-tech clicker. It doesn't require batteries, and it's cheaper, and you don't have to buy it in the bookstore. But there are some reasons I like cards, even apart from, and in some ways better than clickers. One of them is, in addition to the standard options of being able to vote A, B, C, D, which you can fold your card to neatly show one or the other. If you have it narrowed down between two options and you're not sure, you can vote with more than one using some sort of creative way there. And if you want to vote E, sometimes, not with this question, but in some future questions, there will be an option E. Indicate E by showing a white square. This is to remind me a few things I wanted to tell you about the voting cards. Yes, option E is the white option. I have no idea. If you can't narrow it down at all, you can vote like this, and that's really useful information for me to see, rather than randomly guessing like you would with a clicker or by holding up one letter. Tell me that you're making a wild-ass guess. And if I see a lot of those, even if I only see one of those, that's still useful information for me. And a clicker doesn't let you do that. These are going to be used every day in class except for exam days, so bring it with you every day. This is your copy for the whole semester. Get it out before class. Sometimes we'll start off class with a voting question and it just saves a couple moments, a dead 30 seconds while we wait for everyone to unzip their backpack and get theirs out if you already have it out. And if you forget yours, here's another thing you can't do with clickers. If you forget yours on a given day, no problem. I'll have a set of spares up here at the front table, and you can grab one before class and borrow it for the day, and then leave it with me, and then bring yours next time. I don't have enough spares to give everyone a new one every day, so we'll quickly run out if people borrow and don't return. But if you borrow occasionally and return, we'll never run out of spares. If you lost yours entirely, then you can print out a new copy. It's posted on our course website as a PDF. Just make sure to print it in color. It's more useful for me if I can quickly distinguish the colors visually. And I know color copies aren't cheap, so that's incentive to not lose it. Or if it just happens once, you could probably sneak a spare and keep it for the semester. But don't do that more than once or we will run out. We'll use these for voting and make it simultaneous and anonymous for maximum efficiency and learning benefit. To make sure that your peers around you are not influenced by your vote, I will have you hold up your vote on a count of 3, so that's how we'll do it simultaneous. I'll give you some time to think about a given question, and then I'll count down 3, 2, 1, vote or something like that, and then to make it anonymous, hold it here, right against your collarbones, not down here because I might not be able to see it if it's blocked by someone in front of you, but also not up here because the people behind you can see what you're voting, or rather they can see the opposite of what you're voting and might be able to deduce what you're voting, and not out here. So just right here. And then if someone wants to copy what you're voting and they're looking around like this, they're going to look really conspicuous and I'll make fun of them. No, I won't make fun of them, but people don't generally do that. The simultaneity and anonymity is helpful for capturing your individual thoughts, uninfluenced by your peers. And at the end of the semester, if you manage to hang on to your voting card all semester, and I hope you will, I'll collect them and use those as the stack of spares for next semester's class. But I wanted to give everyone a shiny new one so you know it doesn't have any germs on it already, and you get the satisfaction of making those first crisp folds. And if you decide to drop the class, I completely understand our schedules change. Could you give me back the voting card so that that's one less color copy that I have to pay for, and I'll put it in the stack of spares. And you can either just leave it on the back table so you don't have to talk to me in person and say, hey, I'm dropping your class, bye. Or you can just leave it on the front table or give it to a peer surreptitiously. So let's try it out. Go back to the question. Hopefully you've had enough time to think which your intuition tells you is smallest. Prepare your votes. Regardless of the size of the picture, mind you, I'm asking about the size of the actual physical object out in space. 3, 2, 1, vote. Okay. I'll confirm the answer in a moment, but first I want to ask which one you think is largest. Three, two, one, vote. Okay, well, a bit more split of opinion here. Well, I definitely will confirm the answers with you in a moment, but instead of me just telling you the answers, and moreover, instead of me just telling you the definition for the 4 objects depicted there, star, planet, galaxy, and universe, this is on our to-do list as 4 definitions. I'm going to get you more actively involved If you already have your workbook purchased from the bookstore, anybody have their workbook already? Raise your hand. Okay, a handful, great. Get it out. You're going to be doing the worksheet on page 101. If you don't have your workbook yet, that's okay. I understand it takes time to get all your books. I happen to have a printout of that worksheet, so I will have the LAs distribute those. So everyone gets their own paper. Put your name on it. And work with a partner. Get to it. If you don't have the workbook, raise your hand, and the LAs will give you a worksheet. Find a partner. You might have to get up and move if there's not a partner near you. I know the room is steep, so it's hard to work with someone in front or behind you, so you might have to move sideways to get someone next to you. Page 101. Even though everyone has their own paper, work with a partner to talk about your answers and compare. Anyone else need a worksheet? Okay, thank you. Raise your hand if you're finished with 1 and 2. Wow, a few speedsters already finished. Compare answers with your neighbors, and of course, do number 3. I've turned the flipped app on break for any of you who are already using it, so feel free to look up any of these object names for number 2 on your device. You're not expected to know all of them already, or even most of them.
Is that the textbook we need?
This is the workbook.
Okay.
Let me grab you one.
Thanks. Thank you.
You're welcome. Raise your hand if you're finished up through number 2. Okay, we're not quite at the halfway mark, so take a few more moments. If you are finished, keep working on number 3. List as many as you can think of. Anyone else need a voting card? Let me check again. Raise your hand if you're finished with number 2. Okay, well, we're well past the halfway point. The way I do these worksheets, we're going to do them not every day, but often enough that you should bring your workbook every day. This is what it looks like. It's $24 in the bookstore, $23 and some change. And everyone needs their own copy. If you do have your workbook already, by the way, write your name on the inside cover or the first page or something so that you don't lose it and then have to go buy another one. If you don't have yours today, that's fine. We gave you a worksheet, but we won't have those spare printouts of the worksheets every time. So bring your workbook starting next time. And this is the only required item that you have to buy this semester. There are some books that are suggested additional resources that are optional. If you're not sure whether or not to buy them, try not buying them and see how it goes. And if you feel like you need more resources, then go buy them. But this is the only really required one. Let's get back to the question. Well, before we confirm the answer to this, let's make sure we all answered the worksheet questions correctly for number 1, just the matching. Go ahead, and I'm going to have you read out loud in unison the definition of a star. Go ahead. Good. And this is a picture of the star that's closest to Earth on the right. What's the name of that star? The sun. That's not how it would look to your eye, by the way. And you should not look at the sun with your unprotected eyes, especially not for extended periods of time, because it hurts. You'll know that because your blink reflex will kick in. And as long as you don't suppress that blink reflex or ever point a telescope or binoculars at the sun, then you won't damage your retina. On the left is just a picture of a field of stars, an area of the sky showing lots of stars in the night sky now, so you can see the little separate blips. They're stars just like the sun. They're just a lot farther. That's why they look small and faint. I'll leave the lights at a medium level for a moment so that we can better see the upcoming pictures. Okay, give me the definition of a planet. Go. reflected light is evident in the picture on the right, because if the planet were shining by its own internal light, it wouldn't have a dark side. Stars don't have a dark side because their light comes from within. Planets and moons, this is Earth and our moon, real image, by the way, of course, taken from very far away, so that the moon is kind of way in front of the Earth here, which is, they're kind of lined up, which is why they look so close together. In real life, they're actually pretty far apart if you saw them from the side rather than partially aligned like this. Both of those are illuminated by light from an external source. And what is the source of that light? Go ahead and say it out loud. Sun, yeah. The sun's not in this picture, though its light is. The sun is off the edge of the picture. In which direction? Point. Yeah, it must be off that way because the light's coming in this way. Now for this picture on the left, what planet is that? Saturn, yeah, the one with the rings. I just asked because some people learn that in grade school, so a lot of people just know that off the bat. This picture is a real photo as well, and it was taken where the direction of sunlight is coming in from more or less behind the viewing angle of the camera. And so it looks fully illuminated, but if we could see it from the back, it would look dark because there's not sunlight falling on the back. You can kind of see, let me see if I can zoom in on it here, if you look carefully. A bit of a shadow of the planet Saturn on its ring right there. And you don't see that shadow on this side. So that tells you that the direction of sunlight is very slightly from the right, and the shadow is stretching a little bit to the left. Cool. What's the definition of a galaxy? Go ahead. Yep. We'll have a whole lecture or two about galaxies later in the semester. And we'll talk next time about how many stars. I say it's a huge collection, but we're going to quantify that next time. And lastly, universe. Oh, I guess that's not lastly. Penultimately, universe, what's that? Yep. And moon is also on the list. I'm not going to make you read that one because it's the only one left. It's the smaller body orbiting a planet. And I already showed you a picture when I showed planet of Earth's moon. And some of the planets in our solar system have moons. Not all. Mercury and Venus don't, but the rest do. Now, you might have more confidence going into answering this question instead of with the cards. This time, let's go ahead and answer this one out loud, which is the smallest. B is correct. Planets are smaller bodies orbiting stars. And moons are smaller still, but I didn't show a picture of a moon. If I had, that would be the smallest. There is some ambiguity too, because there are some moons that are comparable in size, and who knows, maybe possibly some that we haven't discovered yet that are larger than whole planets. And so I didn't want to get into that ambiguity, so all planets are certainly smaller than all stars. And which one is the largest picture there? Say the letter. D is correct, and that represents universe, although I can't show a picture of the whole universe because it surrounds us on all sides. And this is an actual photograph of the sky, but just taken in one direction. So clearly there's no way to show a picture of the whole universe around us. There are ways to show panoramic images, even 360-degree images and 180 up and down. You can show the entire sky around you with lots of stitched together photographs and project that forward onto a map of the sky, and such images can certainly be made, and I'll show you several throughout the semester. But even that doesn't show the whole universe because it doesn't show how far out the universe goes in every direction. There's no way to take a picture that captures the extent of it in 3 dimensions, though we can capture a projection of at least the nearby stuff that we can see in a 2-dimensional representation. So that's a little snippet of how we will be doing the voting and how we will be doing worksheets sometimes. To give you a starting place, a bridge from common experience out to the large sizes of things culminating in the entire universe being the largest thing that we will discuss this semester. We're going to start with a scale model, a classroom model that's used sometimes in grade school, middle school, or high school. This is called an orrery, O-R-R-E-R-Y. You don't have to know that, but some people are always curious. It's a model of the sun, Earth, and moon. The purpose of this model is to show how these objects move relative to one another. And it has these gears on there, and a well-made one will even have a gear ratio that makes the moon spin around the, orbit around the Earth the right number of times for the Earth orbiting around the sun. So it shows the motions. There are some ways in which this model is flawed. It's not perfect. In three-ish really glaring ways. Let's nitpick. Tell me some flaws that come to your mind. I see a hand way in the back there, second to last row. Yeah, the size is way off. The sun is supposed to be way bigger than the Earth, not just slightly bigger like this model shows, okay? So the relative sizes are terrible. What's another? Yeah.
How close it is?
How close? The relative distances. And those we're going to fix in a moment. The relative sizes and relative distances would be impossible to practically represent with a model that you could both fit in a classroom and actually see the objects. Any subtler flaws that you might spot? Sometimes people come up with these really detailed ones. What do you think?
Looking at the way that the machine should work, it looks like it's going to have a circular orbit, not elliptical.
Yes, the way this mechanism is built, since it's fixed on a rigid metal rod here, that constrains it to have a fixed radius all the way in Earth's path around the sun, which would make it a perfect circle, perfectly circular path. Earth's orbit around the sun is not perfectly circular. It's darn close. It's only like 3% off, but it's not perfectly circular. And this model cannot show that. Ditto with moon's orbit around Earth. Anything else? Those are the biggies. I don't actually have another one in my mind, but I didn't want to close down your thinking if you had another one. Okay, well, let's fix the two most glaring and first stated flaws, the relative sizes and distances. I'll replicate that model here in our classroom, and I'll use this to represent the sun, which is about the same size, near as I can tell, from that model pictured there, just looking at the meter sticks in the background. And this is, I don't know, like 10 centimeters across, roughly. Ignore my scribbling on it. I defaced this model last semester trying to illustrate something about latitude and longitude and office hours, and now I can't get it off. This is 10 billion times smaller than the actual sun. So the map scale of our reality to model here is 10 billion to 1. How would we proportionally scale down the size of the Earth to more accurately represent reality? I have with me some possible objects here. And the range of sizes from this, it's about 5 centimeters across, and you can see it relative to the size of a pen, say. Got a golf ball, and then some smaller things. Well, you know, if that rolls off, it's going to fall in that crack there. Here, let me use this one. You'll just see them in silhouette. Okay, got a marble here. And I have some smaller things that are just going to roll away, so I'm not going to bother. But show me with your fingers or hands how big you think the Earth should be relative to the size of that sun. Like this, like this, like this, something like that. You know it's smaller, so you shouldn't need your arms involved here. Okay, go ahead and hold up your size. Okay, looks like just about everyone is using fingers and not hands. The correct answer is like this. I'm trying to have as small a gap between my fingers as I can. Let me draw it. It is smaller than this dot here. It is a millimeter, so about the size of a ball point in the tip of a ballpoint pen, like the period at the end of a sentence in regular textbook size print. Okay, so that's our Earth relative to this. I just want you to visualize this here and get this in your viscera. Now, how far away should it be? Let's put the Earth, put the sun right there. Will it balance there? Yeah. Point where in the room I should stand. Say I'm going to walk this way. How far away should I stand with my tiny ballpoint Earth to be the right scale distance? Go ahead and point somewhere in the room. Okay, I'll start walking. Let me pace this out here. I'm going to try to take a 1 yard steps, which is slightly larger than my natural stride. 1, 2, 3, 4, 5. I actually have to turn a corner here, which is going to introduce a right angle. Ignore the right angle. Pretend I'm going away as the crow flies. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So right about here, as the crow flies. This is my pinhead-sized Earth. There's my gigantic star. And what's between Earth and Sun? Nothing. Virtually nothing. Mercury and Venus are there, but they're even smaller pinheads, almost microscopic at this scale. And remember, Earth is orbiting around the Sun, so it's going just as far on the other side as it is on this side. So the Earth's orbit would not fit in this room. Would probably fit in Osmond Lab, but not in this room. The rest of the planets in the solar system, we already passed Mercury and Venus on the way. Couldn't see them. Well, we probably didn't physically pass them. They were probably somewhere else in their orbit. But anyway, they're down there somewhere. Mars, Jupiter, Saturn. Well, Jupiter is the biggest planet. It's the marble that you can see on the overhead projector there, the smallest object. That's Jupiter, but it's a marble, not the size of the projection, the size of your pinky fingernail, maybe your pinky finger from the joint down to the tip. That's Jupiter. And its orbit is probably still on campus, but you would certainly get tired jogging that far. Well, you're in good shape. I would certainly get tired jogging that far. And the rest of the planets would be also scattered around campus and getting to the periphery of the solar system out by Neptune, Pluto, and the Kuiper Belt. That would be off campus. All those little specks would be scattered over a square mile. How about the next star? That's our sun, remember, a star. There are other stars out there in the universe. Oh, that's just my phone reminding me to let you guys stretch your legs and have a little break, which I'll do in a moment. But the next nearest star to Earth after the sun is Proxima Centauri. It's in a binary system with Alpha Centauri. How far away do you think that would be? Picturing it as this size, our solar system, just the planets around our sun, scattered around campus and State College. Where would the next one of these be? Bellefonte, Pittsburgh, Cleveland, Chicago, Seattle. Nope. Try London. I know I went the other direction. Now we're going east instead of west. London. It would be 3,500 miles away. That's the next closest star. And between our sun and Proxima Centauri, nothing. Well, the couple of specks that are orbiting our sun, and if there are any specks orbiting Alpha Centauri, maybe, but otherwise nothing. Why am I doing this? Space is big and mostly empty. Not entirely empty. We got to have something to talk about for the next 15 weeks, and we will. But I do this visual model because I hope it boggles your mind, frankly. I hope some of the things you learn this semester will boggle your mind, like they boggle my own. One of the things in particular that I hope you take away is the immense scale of the universe, how huge everything is. We're going to talk about planets, stars, galaxies, and the universe, each object being vastly larger than the previous. And when we get to the universe itself, our discussion of that will reveal that it is so incomprehensibly huge that we don't even know how big it is. We can't even see it all. We will never be able to see it all. Ever. Frankly, one of the things I love about astronomy is it puts me in my place. Even when my life seems so big in my mind, so vivid and real, my problems seem so immediate and consequential, astronomy reminds me that I'm tiny. And I think a dose of that humility is good for me personally, despite my imagined self-importance and my mundane daily concerns. Thinking about the universe and how full it is of wonder and still plenty of mystery makes me feel lucky that I'm here to be able to witness even a small corner of it. And there's always more of it to learn. So enough philosophy. Time for some pragmatism. We're going to take a little break so that you can stretch your legs, inquire about, or sign up for, if you're interested, this flipped thing. Talk to your neighbors, talk to the learning assistants, and I will turn flipped, speaking of, on a break so that you can feel free to check in with your devices. For the next few minutes, I'm going to give us a 4-minute break today, and then we'll resume the class then. Okay, let's come back together. All right, looks like our flipped break is over. So let's get practical for a bit. Syllabus and first assignment. Syllabus is online. I'm a tree hugger and really into conserving resources. So like most things in this class, the syllabus will not be on a paper copy. And go on Canvas to read it. Not now, please. It's long. Apologize in advance, but there's so much useful info in there. And to make it a little less painful, I've made a second assignment, syllabus scavenger hunt. And you get 2 tries, which will be the case for all of the homework assignments, and only your higher score counts. And you can be looking at the syllabus or flipping back and forth between the syllabus and the assignment while you do it, so you can just look up the answers. So that will give you some incentive and reward for actually going through the syllabus carefully. It will describe some of the things we'll be doing in this class, such as the voting cards, which I demonstrated, but that'll tell you a bit more about that, and more about the flipped app and the workbook. And it'll also mention about how I draw names from a hat, which I will now demonstrate for the purpose of giving out some cool Astro prizes. Next time, I will give everybody the opportunity to choose whether you want to opt in to having your name in the hat. It's an opt-in system, but for this class, for this lecture period, I didn't have the opportunity to do that yet, so I just put some random names here from the syllabus to give you a cool prize. Is Thomas Parker here? Calling names from the hat and having you respond is one way that you can get participation credit in the class. In addition to getting the cool prizes, I have NASA stickers and space pencils. Thomas Parker here? Which would you like, a NASA sticker or a space pencil? NASA sticker, all right. Could I ask you guys to help me hand out some of the prizes so Thomas doesn't have to come all the way down here? Here you go. Thomas would like a NASA sticker. Here, take a couple pencils in case the next person wants a pencil. All right, who else are we going to have get a prize today? Yeah, the NASA stickers are pretty cool. All right, Raheel Hadi. Is Raheel here? There's Raheel. Hannah, Raheel's on your right. Give her whatever she wants. All right. Ian Brannon. There's Ian. Allison, Ian's behind you. Give him whatever he wants. Let's do a couple more. How many prizes we've got left here? Erin Fisher. There's Erin. Whoever's closer. Give Erin whatever she wants. And let's do another one. I got a few more names I threw in here. Emily Nash. There's Emily. All right. Give her a prize. How many prizes do we have left? We have 4 pencils. I guess we're out of NASA stickers. I'll restock on NASA stickers for next time. But Caitlin Wolf gets a pencil. Austin Bailey gets a pencil, and Anna Meyer. We have Anna? Everyone's here. All right. I guess I have 1 pencil left over. That's all the names I put in the hat for today. But I'll have all the names next time after I give you an opportunity to opt in or opt out. In the future, I won't be drawing names just to give out fun prizes, but to answer questions. And there will be, as you'll see in the syllabus, always an opportunity to talk with your neighbors before having names drawn from the hat, so you can discuss and have some time to think about what you would say. Another practical matter, and we can use the voting cards for this. I'm curious how often you check your email. If you have your Penn State email forwarded to another address, that's fine. That counts as checking your Penn State email. Prepare your votes. 3, 2, 1, vote. Oh, awesome. Okay. I'm seeing mostly A's. Looks like about 85, 90% A's with a smattering of B's. You guys are fine. I saw at least 1 C, and I'm not sure if I saw any D's or E's. Bump that up so you're checking it at least once or twice a week so that you don't miss any announcements that might come out. And another way to get that information is just to check the Canvas page, because anything I send out as an email will also be visible on your course inbox messages here, which is separate from Penn State email, but I tend to do both. If I'm going to do one, I'll do the other, just so I catch everyone. And you'll also want to check the Canvas page at least twice a week so you don't miss any upcoming due dates, because this is where you'll do all your homework assignments. And you'll see announcements like this welcome one that I posted as an announcement yesterday. And actually, if you turn on notifications in Canvas, you will get the announcements as emails too, and then you won't miss anything. I just don't want you to miss anything. Modules. I know that some of you have already been looking on here because a bunch of people have already done the survey. This astronomy class survey, which you also will see over here on upcoming due dates, right here, is the first assignment in the class. So that's what I'm referring to when I say first assignment on our to-do list. It's due before Thursday's class. For regular homework assignments, you will get more lead time. You'll get 6 or 7 days to work on them. But this survey is different. It's just a survey. I don't want it to be on schedule with the regular homeworks because it's just different in every way. You don't get 2 tries and counted for only the higher grade, and it's actually not graded for correctness anyway because it's a survey. It's graded for completion and putting in a good faith effort, which Canvas times you when you're doing it, and if you do it too fast, it'll know that you didn't read the questions. So take your time and just do it honestly, and you'll be 100%. So that's the first assignment, is this survey. And some of you have already started looking ahead to assignments due next week. There's a multiple choice homework posted already, and that's the syllabus scavenger hunt that I mentioned, and a discussion assignment. So that's where you'll get almost all your assignments on Canvas every week. The syllabus, you can click these tabs on Canvas from the privacy of your house too, but everything's hopefully easily navigable. And it shows pictures of what the workbook looks like, so you can be sure you get the right thing at the bookstore. The only thing you have to buy. These are the recommended texts. They're on reserve in the library in Davy Lab, so you can use them for free if you want to. Not buy them, but if it's more convenient for you to buy them, you can do that too. Email. Okay, so the one reason the syllabus is long, in addition to going through all the standard stuff about exam dates and procedures, standard multiple choice exams done in class, and participation and stuff like that, it goes into a bit of the philosophy of why I build a lot of interactivity in to the class with these worksheets and the voting cards and stuff. And something I take really seriously because I want you to learn. And a lot has changed about how teaching and learning is understood and practiced in the best cases since I was a kid. We used to think, teachers used to think, learning scientists used to think that knowledge was just delivered to people, like this cartoon humorously depicts here. Turn to your neighbor and brainstorm as many fallacies with this model as you can in the next minute. Go. Take about another 15 seconds. Okay, let's hear some of the things you brainstormed. Who can share one thing from their list? Yes? The cartoon shows that everyone learns the same way. Not true with real people. Thank you. What's another?
The learning is straightforward and you can't interpret it yourself.
Yep, there's no assimilation or interaction with the green slime that's being depicted there. Not so with learning. No interpretation? What else? Let's get at least two more. Yes? That it only takes one example or one deposit of the knowledge into the head? Not so? Yes?
Takes no effort from the student.
Takes no effort from the student.
Knowledge is being transferred uniformly.
Knowledge being transferred uniformly. Anything else? Yes? That you're only going to learn it one time. One and done. Thank you. That's an excellent list. Most of what you said lines up with the results from learning research. Real learning, meaningful learning that sticks, should not be a one-way transfer of information. It's better when you interact. And when you can articulate your thoughts, patch up little holes, build a stronger foundation, and all that happens better when you're conversing with a peer or with an LA or a TA or an instructor. Learning doesn't happen when you're passive. You have to be doing something. To be sure, you can passively sit and listen, and some information will get in there, but that tends to create shallow and fragile knowledge and not real connections and deep understanding. And your brain is not empty. As the third item discusses, prior knowledge is important. Everything you take in encounters a whole wealth of world experience that you've built up already throughout your life. And you need to find a place to connect new stuff you're learning for it to actually stick and have some meaning. When it's just isolated facts, and to be sure you can memorize isolated facts, but those aren't really valuable to you. When it connects and links with other things in your mind already, or things in your experience and relevance in real life, then it's meaningful, and that's more valuable for you, and that's what I want you to get out of college and anything you learn, and yes, even stuff in Astro 1. I will endeavor, this is my challenge, to find ways to show you how it's relevant to you and your life and how the skills will be useful. So I'm going to take advantage of these things and try to make Astro 1 not like this, but something valuable for you. If I didn't take advantage of these principles, but did pure lecture to you, which feels good for me, professors love to talk, feel good for you, everyone likes to just listen to a well-crafted lecture. It sounds like a story, it's smooth, it's easy, you can even take notes and jot down things, but still, it's pure lecture. If I did that, even if I were a great lecturer and practiced and polished every lecture ahead of time so that I could deliver it perfectly, how much should you expect to really learn in the deep and meaningful way? It's not zero. I didn't even put zero as an option up there. You'd learn something, but how much? Sometimes our voting questions will be prediction questions. Sometimes they will be reflection questions. So let's predict. 3, 2, 1, vote. Okay, I'm seeing a range. Lots of B's and C's and D's. Not so many A's and E's. Well, the answer is 25%. So that was, wait, what letter was that? D. This graph shows actual data from a real study, a groundbreaking study, actually, with the surprising, even shocking result of how little students learned deeply, demonstrating true understanding and not just ability to regurgitate information on a test. This is number of students, and they studied 6,000 students at a variety of institutions, including Ivy League colleges and ranging to public and private and community colleges. And this is how much they learned. Learning nothing would be 0, so that's not even shown on this axis. Learning everything that was available, everything that was taught, would be 100% or 1.0, and so that's not even shown, but this is kind of middle of the range. This is learning half. It's more like a quarter. Most students learned only 25% of what was available to learn, what the class was teaching. And those are some great teachers, great lecturers. So this is for pure lecture. This is for interactive engagement, where the teachers did stuff like worksheets, voting cards, making you talk to each other, brainstorm, making you answer out loud, having you ask questions, and having just more of you doing stuff during class. It's not perfect, but it's higher learning. There's more of a spread, so it also depends on how much the students put into it and how much the professor inspires them to want to try, and that's my job. And also depends on whether I implement these strategies well or not. So I've been practicing for many years, and I'm going to try to implement them well and hopefully have well-crafted activities to help lead you through a progression of learning. So this is the research basis for why I do my class the way I do it, because I want you to learn more and get something of value that will stick with you and not just memorize, binge, intellectually speaking, and then purge after the final. So that's my sales pitch. If you do this stuff, and including doing the drawing names from a hat thing there and being willing to answer and talk to your neighbors when I ask you to, if you do that stuff, you will learn more. All right, show us those big ideas is next. These are the most important concepts from the whole semester. They're things that either come up again and again as themes, or they're things that even if they come up just once or twice, I think they're important enough to deserve a place on this list. Science, and by the way, I'm doing this on the first day. I'm going to do it again on the last day to bookend the course of the big ideas. Here's what I want you to look out for, the things I hope you remember 90 years from now when your little grandchildren are sitting on your knee, and great, whatever. And they're not the details of definitions of things like you did in that workbook page before. Science is an intellectual pursuit distinct from the other worthy, many other intellectual pursuits, because science relies on evidence. Making predictions, gathering evidence to test those predictions ruthlessly, impartially, without bias, and being willing to throw out or revise your explanations if the evidence doesn't bear it out. Particular to the science of astronomy, light is the most valuable tool that astronomers have. We can glean a wealth of information from light. It'll come up many times. We'll have several lectures all about light. We can learn the temperatures of things, what they're made of, and how they're moving without ever going there, just by studying the light that comes to us. Look-back time is a phenomenon that, because light takes time to travel across the vast distances in space, we see things out there as they were in the past. So we're looking back in time when we look out in space. Gravity is one of the 4 fundamental forces in the universe, and the only one we're going to talk about in this class, because it's the only one that matters on the large scale. The other forces either only work on the very short scale, the strong nuclear force and such, and the weak force, or they cancel out on the large scale, like the electromagnetic force tends to cancel in bulk matter because there are about as many positive charges as negative, and so bulk matter tends to be neutral, so electric forces don't matter, but gravity does. Gravity doesn't cancel, so it matters on the big scale. It dictates how everything moves in the universe and how things are formed and how they die. We are star stuff. That's a shorthand notation for me because it's a near quote from Carl Sagan, my hero, who said we are star stuff to convey that the stuff that we, people, are physically made of comes from atoms that were created inside of stars. The iron in the hemoglobin in your blood cells was created inside of stars. The calcium in your teeth and bones was created inside of stars. The carbon and oxygen in the air molecules and in every substance you take into your body, food or water, those atoms were all created in stars. The universe is dynamic as opposed to static. Static means stationary, unmoving. Dynamic means moving, changing. And it's not obvious when we look at pictures of things in space because they're so far away that any motion that they have, and they do, is not immediately apparent to us. And also things that are really big tend to move and change over very long time periods, so we don't notice it. Even when we look at something again and again over the course of years, we might not notice the changes, but the universe is changing, often on long time scales of thousands, millions, or billions of years. And the last one, I tried to illustrate for you with our scale model before that space is big and mostly empty. We're going to spend the next 15, now 14 and a half weeks talking about all the stuff that is in space, the stars, the planets, the moons, the asteroids, the quasars, the black holes, stuff that wasn't even on the worksheet from today. So I like to pause on the first day with this activity that we already did and with this last item on our to-do list, on our big ideas list. We still have another on our to-do list, to at least acknowledge all the stuff that isn't in space, which is a strange way to phrase it. Perhaps I should say all the emptiness that isn't stuff in space. It's mostly empty. Cool Pics is a slideshow. No words, and you don't have to take notes on this. I do encourage you to take notes during the regular part of lecture, so I hope that you were taking notes earlier today, and will do so every day. If you didn't, get notes from a classmate perhaps. But don't have to take notes on this. I want to give you a visually pleasing and hopefully inspiring slideshow to help you get excited about the topics to come. These are all real pictures. This is our sun, taken with a telescope, so it is able to get much higher resolution than we would get with our eyes and see more details. And also it's taken with special filters to bring out some features that our eyes would not notice. This granularity you see, sometimes bright where there is material bubbling up, sometimes dark where there's material that got trapped on the surface and cooled off and hasn't yet intermixed with the rest of the hot material in the sun. Still pretty hot, but maybe a few hundred or a few thousand degrees cooler. And look at these loops. Some of them huge. If you remember our scale model of the sun compared to the size of the Earth, this was our sun. The Earth was a pinhead. That's about a ratio of 100 to 1. It's actually 109 Earths would line up across the face of the sun. By volume, since volume goes as diameter or radius to the third power, that means 1,000,000 Earths would fit inside the sun, three-dimensionally. But one-dimensionally lining up, it's 100 to 1. So the size of the Earth is smaller than this gap in this loop. It's actually smaller than this gap in this loop. These coronal mass ejections and these prominences, a lot of times they spray up into space here and some of the material rains back down, but sometimes they're violent enough that the material sprays out into space and doesn't come back. And then we can have these solar activity, actually charged particles and material that can come all the way to Earth. By the time it gets here, it's not like going to hit anything and dislodge anything, but the charged particles and the highly energetic particles can actually interfere with the electrical systems of our satellites in orbit, the space station, the electrical grid on Earth. Occasionally, if enough stuff gets through the atmosphere, it can actually interfere with the electrical grid, and power outages have occasionally happened in cities because of solar storms. But most of the stuff rains back down on the sun. I'd just like to point out that our sun's not a boring, quiet place. Not sound quiet speaking, but just activity kind of speaking. So that's one star, but we're going to talk about stars as a population and why they have this variety of properties that they do. Stars come in different colors. We'll talk about why. Turns out it's from their temperature. The hotter stars are blue, the cooler stars are red, but cooler stars are still hotter than the hottest oven on Earth. We'll talk about why some are brighter, some are fainter. Here is a view of a bunch of stars in the night sky. And this was taken on a moonless night, and in a very remote area. So there's no light from moon or city lights or human-produced lights. And so the light falling on this landscape here, and it is a long exposure photograph in order to bring out some of the faint things, but all of the light falling on this landscape is from the stars. So that's pretty cool. Here's a constellation. I'll show you a view of it in the next slide too. It's kind of laying on its side here. Here it is. 2 stars on the top. Those are the shoulders. 2 stars on the bottom. Those are the knees and the feet. And across the middle here, there's 3 stars in a row. That's the belt. Anybody know the name of this constellation? Go ahead and say it out loud if you know it. Orion, yeah. The 3 stars on the belt are usually the easiest, first thing that I spot. And then dangling down below the belt of Orion here is the sword, you'd say. And that's a little hard to pick out with your eye because it's a lot fainter than the belt stars or the shoulders and knees. I've been reading a lot about Betelgeuse in the news lately. It's fluctuating in brightness. It's dimmed a lot over the last few years by like 60%, and some people are speculating, is it about to go supernova? Who knows? It actually might. It could happen tomorrow, or it could happen 1,000 years from now. We cannot say for sure until it happens. Here's another view of Orion. It shows more with a telescope using a different kind of filter of this wispy gaseous material, and actually reveals a stellar nursery in the sword of Orion. Sometimes, depending on what wavelength of light you use and what kind of filters and what comprises the clouds, sometimes the clouds look dark instead of bright if they're blocking light from behind. This is not a hole in space. This is a dusty, sooty cloud with tiny little solid particles that block the light of the stars behind. Stars are being born inside that cloud and inside these little striations in this larger cloud. Stellar nurseries are everywhere. Space is empty-ish. But in addition to the stars and planets, there are also these wispy clouds where stars are born. Here's a cloud that shape tells us that it's actually where a star just died. This is an expanding bubble of gas. The last gasps from a dying star sent this slow-moving wave, not a shock wave, it's not fast enough to be a shock wave, but this expanding shell of material that the dying star expelled. Our sun is going to do that in about 5 billion years. Here's another star that just did that in an asymmetric fashion. Makes it kind of pretty, don't you think? Here are some stars forming from the remnants of stars that previously died. The more that wispy material. And here are some stars that were born close together in a cluster. Stars often are born in these multiples and not individuals. Galaxies, much, much, much larger than star clusters. We'll get to those in maybe the last third of the semester. And sometimes galaxies merge together, crash into each other. We'll talk about that. And we'll talk about the whole universe, how big it is, how it started and why we think that. And I'll close with this picturesque view of Saturn now taken so that you can see the shadow on the backside of Saturn where the sun isn't hitting and the shadow of the planet on its own rings. Amazing photograph that just pops the eyes. Well, thank you, everybody. You don't have to turn in anything. Take your voting card with you, bring it back next time. Keep your worksheet. When you get your workbook, just tuck it inside there. I'll see you on Thursday.